Alrighty, lads and ladies, welcome back to the wonderful wild world of calculus. Today, as promised, we are digging full force into integration by substitution, which is our sort of backwards chain rule that we introduced last Friday. I'm going to give you the sort of formal theorems, and yeah, this is sort of our last big hurdle in this class. So this is an exciting day. Once you master substitution, the rest of the class really is smooth sailing. There's only one section that remains after this one, and we are going to spend pretty much all week on this section. It's one of those skills that, especially for those of you moving into Calc 2, you really need to get down because it's a very fundamental skill, just like the chain rule in this class has been a very fundamental skill. U sub is going to be one of those things that you just do all the time in Calc 2. So this is MAC2311, section number 004, which is a Calc 1 class. The date today is the 11th of April, 2022. And today, Wednesday and Friday, it's all about integration by substitution, aka U sub. You'll see and hear, especially if you Google around about this sort of stuff, watch YouTube videos, blah, 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 people often refer to this just as U sub. I'm going to use different variables than U. We can use the variable U, and I will do that sometimes. But once we get accustomed to it, I'll swap variables around just to try and get us comfy with different symbols, because that's an important thing as well. The big idea is that this is a backwards, so substitution is a backwards chain rule. And what the chain rule says, just a reminder, although I'm sure everybody remembers it, I'm going to state it in some specific notation. If U is equal to G of X, then the derivative d dx of f of U would be f primed of U times U primed, which could also be written as i.e. d dx of f of G of X is equal to f primed of G of X times G primed of X. So what we're going to be doing then is we will use this to integrate functions which look like output from the chain rule. Which look like this, look like something like f primed of G of X times G primed of X. The big thing is that you've got an outer and an inner, and that the derivative of the inner is floating around. So we're going to want to do integrals like this. And the prime on the f isn't so important, but having an outer and an inner here where the derivative of the inner function is also present. And that turns out to be the sticking point. I'm going to go very carefully through the language and everything, the algebra, but the big thing with U sub, the big thing with this backwards chain rule is that you need to make sure that you can find the derivative of your inner function floating around inside your integral. This piece is necessary. And if it's not there, you have some sneaky ways to try and either force it in, or readjust the integral in such a way where you either don't need to make the substitution or readjust in such a way where you can sort of solve for this missing piece. I'll show you what I mean. Before we get to fiddling with anything subtle, let me go ahead and present to you the theorem. I have it up here now. Go back here. So I'll show you examples in a minute. Let me just go ahead and present the rule. Here it is. So in the notation we were using a moment ago, and I'll write this as plainly as I can. Theorem, which I'll just call U sub, says if U is g of x, then we can rewrite the integral f of g of x times g prime of x dx as integral. This would be f of u because u is g of x. And this piece here, g prime of x dx, if you remember what we talked about at the end of class last time, differentials, g prime of x dx would be precisely du. And that's because u is g of x, and if you calculate the differential using the rules we discussed last time, du would be g prime of dx. And once you have your integral rewritten like this, you can treat u as the variable. You no longer have to think about x at all. You can anti-differentiate with respect to the variable u, and that's the game. There is a version of this for definite integrals, which I will discuss with you on Wednesday. For today, I want to focus primarily, at least, on indefinite integrals because there are some subtleties with definite integrals that I don't want to overwhelm you with. So let's begin with a couple simple examples. First, maybe before I do that, any questions about the terminology and notation here? We all know what differentials are. Does anybody want a quick review of differentials? All right. Let's take a shot at it. We'll start simple with something like e to the pi x. So we actually did one very much like this on Friday of last week. Does anybody remember how we did the integral of this form last week? What was that procedure like?
Is u equal to pi x?
Very good. All right, so you notice in the theorem, they say if u equals g of x, this part is kind of built into the theorem. But in practice, when we go to execute this procedure, we must choose the variable u. So we're going to let u be pi x. And I think it's the element of choice. It's a creative step. It's a thing that you have to come up with. And that's what makes this so hard. It's not purely mechanical. Now, after you pick your substitution, after you choose what you're going to substitute for, you immediately calculate the differential. And to do that, you just take the derivative of pi x and you slap on a dx. So the derivative of pi x is just pi. That means if u is equal to pi x, then du, the differential, is pi dx. And I always like to put my little substitution here in a box. And that lets my reader know that the equal signs that are a part of the substitution are not a part of the workflow for the problem. Under this substitution, the integral of e to the pi x dx will become integral of e to the u, but I need to replace the differential dx by its equivalent expression under du. Right? If I'm going to integrate a function of u, the differential needs to be du. So the question is, how do I turn dx into du? And the answer is right here. Du is equal to pi times dx, which means that dx, where can I write this? Over here, color, means that 1 over pi times du is equal to dx. So this is the way most people learn it at first. You solve this differential for the piece you're trying to replace. I'm trying to replace dx. So I solve this for dx. To do that, I divide both sides by pi. And now this is what I can plug in for dx here. So I get e to the u times 1 over pi du. And remember, the differential is always multiplying the whole integrand. So you should read this as the integral of e to the pi x times dx. The dx is multiplying everything there. So the 1 over pi du is multiplying everything here. One over pi is a constant multiple now, right? This whole thing in here is multiplied by the constant 1 over pi. So I can bring 1 over pi out of the integral. One of my properties of the indefinite integrals, constant multiples pop out. And what's left is the integral of e to the u du. And now you approach this as though it's a totally fresh problem. No longer are we concerned at all with the variable x. We're concerned exclusively with the variable u. And I'm asking what function of u, when I differentiate it, becomes e to the u. The 1 over pi is just going to tag along. So whose derivative is e to the u? I saw a quick unmute from Cameron there, but I didn't hear anything.
E to the u.
Yeah, e to the u, right? If I differentiate e to the u, I'll get e to the u. The 1 over pi comes along. It's an indefinite integral, so we slap on a plus c. And you might be tempted to call the problem done at this point. But remember, we were asked about e to the pi x. And if I come around and say, oh, it's 1 over pi times e to the u plus c, people are going to be like, the fuck is this thing? So when you're doing an indefinite integral, at the end, you need to plug back in your substitution. The answer should be in terms of the original variable. So 1 over pi, again, just a constant, that's 1 over pi. e to the u is e to the pi x. And that is now job done. Take any of your known antiderivative formulas and slap a constant in front of the x. They all go the same way. So sine of 2x or cosine of pi x, or any of that stuff, you can play this game with very effectively. But that's not the only place we can play this game. So questions on this example here, on any of the purple steps? Okay. I want to come back and double underline the word need here. This is not optional, right? We cannot integrate e to the u dx. That would not make sense. And you notice I didn't write that. Yeah, nowhere did I mix up any variables. You don't see any integrals that have both variables written. It's important that you also do not do that. It can lead to some very messy mistakes and some bad misconceptions that are quite hard to overwrite once you get into the bad habits. So let's do it in red. Do not get in the habit of mixing variables in your integrals. Things like integral of e to the u dx don't make sense. Number one bad habit when we're first learning U-sub is to write expressions like that, and then just get kind of lost about what is a constant and what isn't a constant, what can pop out, what can't pop out, how you're integrating or differentiating what is a variable and what is not. Very, very dangerous. So the expression I have written in red there at the bottom, the integral of e to the u dx, is total nonsense. It doesn't have any meaning. You're asking for the antiderivative of e to the u taken with respect to x, but u and x are both variables. They share dependencies, but they're not the same thing. So there's not a nice way from where we're sitting right now to make any sense of something like that. Okay, let me draw your attention back up here. We said we're attacking stuff like this. And this g primed doesn't need to be a constant. Here, we can think of e to the pi x as e to the pi x times pi divided by pi. And then I can group that pi. So let me show you an alternate way to execute this substitution, an alternate notation. People generally don't like this as much at the start. They generally prefer to solve for dx and plug in. But the way of thinking about this that I'm about to show you is, I believe, the superior way. So again, we're going to make the substitution u equals pi x. We're doing the same integral. Again, du is going to be pi dx. There's nothing I can do about that. But instead of solving this differential for dx and plugging in, what I can do is think of this as e to the pi x times 1 over pi times pi dx. What I'm doing here is multiplying by 1, but I'm multiplying by 1 in a useful format because it gives me pi dx, which is du. And of course, this piece is e to the u. So without ever going through that rigmarole of solve for dx and plug in, I can go, okay, this is e to the u times 1 over pi du, and it's the same from there. This way of thinking can get you out of more traps than you might expect. But if you prefer to do it the other way, that's okay too. I'll do a combination of two, depending on what the problem flows most nicely with. I'll move freely from one way of thinking to the other. The reason I wanted to show you this is because the g primed here is really this pi, right? G of x is pi x, so g primed of x is pi. And by multiplying and dividing by pi, I'm able to introduce the g prime term that wasn't there originally. All right. I don't want to confuse, so let's try some other stuff. One of the things that I do as a hobby is run the integration bee, train our team here at Santa Fe for the integration bee, and previously ran the integration bee at UF for the UMS. Problems that incorporate the current year are a lot of fun in those sort of settings because they generally give a sense of like something very general, right? Something that could be generalized. So there's nothing sacred about the number 2022, but there's something special about there being a power of x here that is 1 larger than the power of x here. And that's the hint. I cannot split up the square root. I want to be clear about that. This is not the same as 1 plus x to the 1011. Square roots never split up over addition or subtraction. The only way to attack this problem is with a substitution. And what I see is that the derivative of 1 plus x to the 2022 is almost the same as x to the 2021. We'll get specific about what that is, but that's what you're looking for. So here's my outer function, it's the square root. Here's my inner function, 1 plus x to the 2022. And here's the derivative of that inner function, or almost the derivative of that inner function, up to a constant multiple. So can anybody suggest a substitution, thinking of squared as the outer, this is the inner, and this is being like the g prime, the derivative of the inner? Remember, we generally want to substitute for the inner function. So what would I substitute for here?
I'm just gonna guess 1 plus x to the 2022.
Perfect. Yeah, exactly. We generally want to sub for the inner function. And here my inner function is 1 plus x to the 2022. There's nothing wrong with guessing, especially in this setting. So we're going to substitute u equals 1 plus x to the 2022. substitute for the inner function. And then before we do anything else, we immediately calculate the differential. So I differentiate this function and I slap on a dx. The derivative of 1 is 0. The derivative of x to the 2022 is 2022 times x to the 2021. So that differential is du equals 2022 x to the 2021 times dx. I have an x to the 2021 and a dx here. What I don't have is the 2022 floating around in my integral. So what I can do is rewrite my original integral as the square root of 1 plus x to the 2022 times x to the 2021 dx. I have this piece, which is this piece. So if I divide both sides by 2022, I get du over 2022 is equal to x to the 2021 dx. And now this piece is here. So this will be my du over 2022. And this piece will just become the square root of u. So let's write outside again. So this integral can be rewritten as the square root of u times du over 2022. Which is the same as integral square root of u times 1 over 2022 times du. And I can, just like the 1 over pi, I can pop out the 1 over 2022. And I get integral of square root of u du. So that's 1 over 2022 times the integral of u to the 1/2 du. And then that's 1 over 2022. This is now a power rule thing, just thinking of u as the variable. If I add 1 to that power, I'll get u to the 3/2. And if I divide by 3/2, that's the same as multiplying by 2/3. So we have this. And this is the bulk of the work done. I'd like to pause for a moment. Let's do this in sections. Questions up to this step. So picking the substitution, calculating differential, plugging everything in. Problems, issues, questions, concerns, crises, anything up to this step here. Okay. Questions between that step and here? I know this might seem silly, and I'm not patronizing you. Are we all comfortable with this? that dividing du by a constant is the same as multiplying du by the reciprocal of that constant. It might feel silly, but it's a place where from time to time our brains go ka-chunk. That's why I chose to write it like this, so we could have the conversation about this move.
I am, I guess, a little confused because du equals 2022 x to the 2021 times dx.
Mhm.
And then you're just dividing du by 2022 to get rid of that 2022 inside of the du.
Yeah, that's the idea. So when I look at my
Okay.
integral, I realize I don't have this whole thing here. I just have this part inside my integral. I just have this. So if I'm trying to replace dx by its equivalent expression in terms of du, I want to look for as much of this crap as I can find inside my integral. And then whatever isn't there, I'm going to divide over and put with the du. So when I look at my integral, I go, okay, what do I have that looks like this? I don't have a 2022, but I do have x to the 2021, and I do have dx. So let's put those two pieces together. I'm going to use this piece to replace by du, but it's not exactly du. So I need to divide over this 2022. And I see that, oh, du over 2022, that's this piece, right? The highlight piece and this piece are the same. So I can replace this right here by du over 2022 and then figure the rest out.
Okay, that makes sense. Thank you.
The goal is to get rid of all the x's. I don't give a shit about constants because we know we can shove constants out in, split it, whatever. But the variables, that's the scary part. I need to make sure that when I execute my substitution, both where we're plugging in for u and where we're replacing the differential, I get rid of all the old variables. I'll make a little note about that towards the end here, but let me go ahead and finish this up now because we're not quite done. The constants, clean it up or not, it's a matter of taste, but the answer needs to be in terms of the original variable. So I will go ahead and clean up the constants here. The 2 and 2022 cancel to 1011, multiply 1011 by 3, and you get 3033. And then u to the 3 halves, u was 1 plus x to the 2022. So this is going to be parentheses 1 plus x to the 2022 raised to the 3 halves power plus c. And that will be our final answer. Again, as much as we might want to do it, I cannot distribute the 3 halves power to these two terms separately because powers don't play nice with addition or subtraction. That's why roots do not. All right, let's keep going in this direction. One of the great embarrassments of the first, say, 12 weeks of Calc 1 is that even after doing integrals for like 3 weeks, there are still some basic trig functions we can't integrate. And the trig functions are supposed to be our best friends. Everybody knows the derivative of the tangent function. How do you integrate tangent theta? If you run through the list of derivatives that you know, trying to come up with an antiderivative rule, sine differentiates cosine, cosine differentiates negative sine, secant differentiates to secant tangent, so maybe something there, but not exactly. Tangent differentiates to secant squared, definitely not that. So what gives? Nobody in the world of trig has a derivative that is tangent theta. Damn. However, Tangent is by definition sine theta over cosine theta. So my integral is sine theta over cos theta d theta. There is no obvious inner or outer here, right? It's not the most obvious composite function in the world. But using that same sort of trick we wrote down with fractions a second ago, this is the same as 1 over cos theta times sine theta d theta. And now cosine is looking like an inner. This is like 1 over u, where cosine is the inner function u, and sine theta, not exactly the derivative of cosine theta, but real fucking close. And that hints strongly at the substitution u equals cos theta. Before we do anything else, we calculate du. The derivative of cos theta is negative sine theta. So du is negative sine theta d theta. Again, always write your differentials. Don't skip writing the d theta here. Now, sine theta d theta, negative sine theta d theta. One over cos theta is clearly 1 over u because I'm subbing u equals cos theta. Sine theta d theta is the negative of du. All right, if you like, you can say from here, if you multiply both sides by -1, you get negative du equals sine theta d theta, or however you like to think of it. I write the parentheses here because we do not want to give our reader the impression that we're subtracting du. Remember, the differential always multiplies the integrand. So these parens are y's, or you could write -1 times du if that feels better to you. The upshot is a negative will fly out of this thing, and now I'm integrating 1 over u du, which is not terribly hard. Can anybody give me an antiderivative for 1 over u?
ln u.
Very good, the natural log. And we do want to be a little bit careful with our notation. This will be the negative here, natural log of the absolute value of u. And this is one case where the absolute values really are important, because you know that cosine is not always positive, spends half of its time negative. But this antiderivative will work whether cosine is positive or negative. And then finally, we replace our substitution. U was cos theta. Now I do have a little comment here. Before I get to that, are there any questions on any of the steps that lead us to this? Okay, little comment. Tangent and secant are buddies. They're good friends. The derivative of tangent theta is secant squared theta. The derivative of secant theta is secant theta, tangent theta, and we have that Pythagorean identity 1 plus tan squared theta equals secant squared theta. I could go on, but tangent and secant are friends. So where you encounter a tangent, there's going to be a secant somewhere nearby. Wouldn't it be nice if I could keep that connection between secant and tangent going when talking about the antiderivative of tangent? Well, I can. By the rules of natural logarithms, or logarithms in general, the negative of the natural log of cosine is the same as the natural log of cosine theta all raised to the negative first power, which is the natural log of the absolute value of 1 over cosine theta plus c. And 1 over cosine is secant. There are people who are so anal about this that if you tell them the integral of tangent is negative ln cosine, they will give you shit for it. I'm not that guy. Negative ln cos theta is correct. But I think it's much more appealing to say that the integral of tangent is the natural log of secant. For one, there's no ugly negative outside. And for the other, tangent and secant are good friends. I would go as far as to say you should memorize this. This is something you should know. You ought to add integral of tan theta d theta equals ln absolute value of secant theta plus c to your list of known antiderivatives. It will save you time. One of our goals is to get to a place where, like right now, you know the derivative of all 6 trig functions. Wouldn't it be dope if you knew the integral of all 6 trig functions? So here's one to add to the list. And that's just a nice way to remember it, right? Because secant and tangent. Okay. So you ought to add this to your table of known integrals. Because the trig functions have derivatives that relate so readily to one another, they're a great source of fun substitution problems where you're subbing for an inner, which is a trig function. I'll do one more like this, and then we're going to look at some slightly different flavored problems. How about e to the sine theta times cos theta d theta? What do I sub for?
Sine theta.
Very good. Right, this is clearly the inner function. This is like e to some stuff where the stuff is sine theta. And what's better, the derivative of sine theta is chilling right over here. My pen is shit in the bed. Maybe I'll go ahead and bravely use a new variable. In Calc 2, I always use Z for substitutions, never U, because we use the symbol U for something else in integration. So I'll substitute Z equals sine theta, and then immediately calculate the differential dz, which is cos theta d theta. And this one just couldn't be smoother, right? Cos theta d theta is chilling right here. You've got exactly what you need to make the substitution work. So your integral becomes integral of e to the z dz. And that's very nice because e to the z is its own antiderivative. And then we just replace z by sine theta. And now a question. What would I do if this integral didn't have the cos theta term? Or more generally, what can we do if the differential don't match? Even after fudging a constant. I don't mind telling you that the answer to the first question is we wring our hands of the bitch and walk away. Can't do it. Cannot do it in this class with the techniques we have. The integral of e to the sine theta d theta without the cosine theta term is beyond us at this point, and that's okay. But the question, what can we do if the differentials don't match, is one to think about a little bit, because we're not always completely boned. As we saw with the e to the pi x, where I multiplied by 1 over pi times pi to like shove in a piece, we can play those sort of games. The short answer is you get creative. If I wanted to evaluate, so let me phrase this question a little, example a little differently. Let's say execute the substitution z equals sine theta in integral e to the sine theta d theta. We will not be able to finish this. We will not be able to find the antiderivative here. But I will be able to give you an equivalent integral in terms of the variable z. Okay. If z is sine theta, then dz is still cos theta d theta, but I don't have a cosine anywhere. So like any good enterprising asshole, I shove it in. E to the sine theta is the same as e to the sine theta times cos theta over cos theta d theta. You can't stop me from doing that. This is the same thing as integral e to the sine theta times 1 over cos theta times cos theta d theta. Okay, now I've got my cos theta d theta here. But I also have this piece down here. And he's a problem now. You see, the thing is, we have to get rid of all the old variable stuff. We can't mix variables around. So writing this as integral e to the u 1 over cos theta du is nonsense, right? In the same way that e to the u dx is nonsense. But we do have this identity, which means cos theta can be written as the square root of 1 minus sine squared theta. So I could rewrite my integral as e to the sine theta times 1 over the square root of 1 minus sine squared theta times cos theta d theta. And now I can make the substitution go. Now I can do it. Why? Because this piece is going to get soaked up by the dz. This piece is going to go away. It's just going to be dz. And everything else that's left over is in terms of sine theta, which is z itself. So from here, I can write this as integral of e to the z times 1 over the square root of 1 minus z squared dz. And this integral is a bitch and a half. I'm not going to do it. We're not going to do it. We're not even going to learn how to do this in this class. And that's okay. Because the task given to us was to execute the substitution, not to solve the integral. But seeing how to deal with adversity like this is important. And I'm going to show you another flavor of this sort of adversity in a second. It takes getting used to. But the big idea that we must replace every instance of the old variable by equivalent expressions in terms of the new variable. So I had a 1 over cosine theta. I was able to rewrite that cosine theta in terms of sine. And since I'm subbing z equals sine theta, that allows me to rewrite this piece as this piece. And now I have a properly executed substitution. Let me show you a simpler version of this type of problem and see if we can't get there without me showing you. This time we will actually evaluate. what could I substitute for here? See, I saw Evan unmute for a second. Any ideas? Guesses are fine.
I was going to say x minus 3.
Beautiful, perfect, right? That's my inner function here. This square root looking very much like an outer, so this x minus 3 looking an awful lot like an inner. The challenge is, what the fuck am I going to do with this? But let's start writing down the substitution, see what falls out, and then see what we need to do. So this time, maybe I'll let w be x minus 3. I'm substituting. My differential dw is quite nice. The derivative of x minus 3 is just 1. So this is going to be 1 dx. And we usually just write dx. The problem is, if you just plug this in, okay, this piece will become the square root of w. Dx is the same as dw, but what do I do with him? I know I can't integrate x times the square root of w dw. It's nonsense in the same way that e to the u dx was. Can't have a mixture of variables. We must replace every instance of the old variable by the new variable. And the idea is we want an equivalent expression for x in terms of w. So does anybody see how to get an equivalent expression for x in terms of w?
Can it be w plus 3?
Hell yes. Since since w is x minus 3, w plus 3 is equal to x. So my integral x square root x minus 3 dx is going to be the integral of w plus 3 times the square root of w dw. Something you should always ask yourself as you're solving these problems is, did the substitution I make improve the situation at all? Is this integral easier than the integral I started with? For example, just substituting something like u equals x or w equals x, that never changes anything. I'm always baffled when I see people attempt that, because it's like, what were you expecting? But here we did actually change something. W was x minus 3, and we essentially brought this subtraction under the radical out into addition in front of the radical. And I ask you, does that improve the situation at all? Related question, why is this integral hard? Why can't I just write down an antiderivative? What's getting in the way?
The square root.
Yeah, I can't distribute the square root, right? This is not root x minus root 3. That shit don't work. Now there's no addition or subtraction going on under the square root. This is just w to the 1/2. It is a power function, and this does not have any wonky power attached to it. So I can distribute and split up from here. So things have gotten better. This is the integral of w root w plus 3 root w dw. And remember, anytime your integrand is split up into multiple pieces with addition or subtraction, you need to put the whole thing in parentheses, because this differential acts on the whole thing. So just good notation. It might not look like it, but this is a power rule integral. All right, we've had some practice with things like this now. This is w times w to the 1/2, which is w to the 3/2, plus 3 times w to the 1/2 dw. And now it's a power rule. If you add 1 to the power 3/2, you get 5/2. So I'll have w to the 5/2, and we need to multiply that by 2/5. That's the same as dividing by the 5/2 power, plus w to the 1/2 will integrate to w to the 3/2, again adding 1, and then I've got a 3, and I'm dividing by 3/2 or multiplying by 2/3, so that will become just a 2. And it's at this stage where we write our plus c because there's no more integral sign. And then finally, we can replace by the original variable. A little while back when my wife took Calc 2, I remember sitting outside the classroom, actually in my car in the parking lot, waiting for her to come out. It was an evening class. And as kids started leaving the classroom, I was asking them, how'd the test go? What was hard? What was easy? And the professor for that class, who's Professor Nieves here at Santa Fe, gave them almost this exact problem. And all the people who came out complained about this problem being just so difficult. And this was Calc 2. They forgot how to do this shit. They forgot how to handle a copy of the original variable being left after your substitution. And the answer is solve your substitution for the original variable. You can always do this. You can always do this and then plug it back in. So it's a good trick.
Excuse me?
Yeah.
I'm just where it says the 2w with the exponent 3/2. For some reason, I'm having trouble noticing where the 2 came from.
Oh yeah, no problem. So I was a little bit skeezy there. So we're doing integral 3w to the 1/2 dw there, just this piece on its own. That's 3 times integral of w to the 1/2 is w to the 3/2 divided by 3/2, which is 3 times 2/3 w to the 3/2, and then I cancel the 3's.
Got it. Thank you.
Yeah, no problem. I'm sure there are other people thinking the same thing. Okay, we have a little bit of time left. There are some other fun problems that I'd like to share with you before we go. So I'm gonna, well, I guess first, any other questions on this? Okay. Maybe 1 or 2 more. Oh yeah, we haven't done syncing yet. Let's do this first. Yeah. I feel like this is the least obvious of all the ones we've done so far. We could follow the feel of the tangent integral and try to substitute for the bottom, and sometimes that works. This is getting sticky. could sub for 1 plus x to the 6. But the derivative of 1 plus x to the 6 is 6x to the 5. And I just have an x squared up here. I don't have an x to the 5 to give to the differential. This is one of those things that comes more with practice than anything else. But the trick here, and there are variations on this, is that x to the 6 is the same as x cubed squared. So there is secretly an inner function here. If I rewrite this as 1 over 1 plus x cubed squared times 3x squared dx, then we can see that the x cubed would be a good substitution, because here he is playing like an inner function, and here is his derivative ready to get soaked up by the differential. So if I make the substitution, u equals x cubed, du is 3x squared dx, that's convenient. Then my integral will become 1 over 1 plus u squared du. Does anybody remember an antiderivative for 1 over 1 plus u squared?
Arctangent.
Very good. Yeah, this is the inverse tangent function. This is tangent inverse of u plus c. And then we replace u by x cubed. A bunch of variations on this exist using like exponentials. I could have e to the 2u and e to the 2x and e to the x up here. Things with rational powers of x, like 1 plus x squared and 1 plus x cubed and 2/3 x to the 1/2 or something up here. Lots of variations on this exist. So be on the lookout when you have an integral where the denominator is like 1 plus something. See if that something can be written as something else squared, and consider subbing for that inner thing. All right, this last one is a real treat and a real headache at the same time. I mentioned we want to integrate all 6 trig functions. We haven't talked about secant yet. I'm showing you this not because it's something that's going to teach you a technique, right? Every one of these integrals we've done so far generalize nicely to families of integrals, and the trick for spotting the substitution is something that you'll use on lots and lots of problems down the road. The trick for this one is weird, and I'm showing you this problem not because I expect you to generalize the method in the homework or anything. I'm showing it to you because I have a sense of obligation to show you how to integrate all 6 trig functions. Nobody would think to do this, myself and other professional mathematicians included. You're going to multiply by 1 in the form secant theta plus tangent theta over secant theta plus tangent theta. It's bizarre, but it works. It works in a very clever fashion. So I'll rewrite the integral of secant theta as integral of secant theta times secant theta plus tangent theta over secant theta plus tangent theta d theta. Very weird. And nobody would look at this and go, of course. This is now the same as integral of something over secant theta plus tangent theta. The something is secant theta times parentheses secant theta plus tangent theta. Still not really looking any better. But then when I distribute this secant theta upstairs, something cool happens. I get secant squared theta plus secant theta tangent theta divided by, I'm going to change the order of the addition downstairs. You don't have to do this, but it makes it easier to see. So having done this genuinely bizarre bit of algebra, does anybody see a substitution?
Would it be secant?
That's part of it. So if we sub for secant, say u equals secant theta, then du would be secant theta tangent theta. I'd still have this secant squared here. I could write that as u squared, but the tangent down here wouldn't go away. That would be a headache. But the derivative of tangent is secant squared, just like the derivative of secant is secant tangent. So if I sub for the whole bottom, then my differential du will be the derivative of tangent, which is secant squared theta, plus the derivative of secant, which is secant theta tangent theta, all times d theta, which is precisely my numerator. Very sneaky shit. So under this substitution, this integral collapses into 1 over u du. Which we know gives us the natural log, the absolute value of u plus c, which is going to be the natural log of, for whatever reason, we change the order back to secant plus tangent. Usually when writing this, you could write it as tangent plus secant. Doesn't matter. And this is definitely one you want to add to your memory banks. This is not a procedure you want to have to go through every time you bump into the integral of secant theta. So, add integral of secant theta d theta equals the natural log of secant theta plus tangent theta plus c to your table of integrals. And with that, we know how to integrate sine, cosine, secant, and tangent. We haven't addressed cosecant or cotangent, but they go very similarly to secant and tangent themselves. I'll let you work those out. It's nothing crazy. It is the same trick, and similarly, you should just remember the antiderivatives of cosecant and cotangent. They're in your book in that table that I gave you. Perhaps not. No, perhaps not. And I'll give them to you next time. So next time we're going to talk more about integrals by substitution. You notice today we did all indefinite integrals. None of them had bounds. When you substitute in a definite integral, there is some work to do with the bounds. It's not a like just do the indefinite integral and then evaluate. There are some specific steps you need to take to make sure you don't tell lies along the way. I'll clarify what that is. If you want to, you can preview it. If you look in the modules, you will find a little section there titled Why We Always Change Bounds When Substituting in a Definite Integral. If you want a preview of what I'm talking about, you can check that out, but that's what we're going to do next time. So next time on Wednesday, we'll do lots more U-sub, only in these definite integrals rather than indefinite integrals. It'll mostly be the same, so there'll be a lot of practicing grouping differentials, algebra, stuff like that. But there will be some special attention paid to graphs, preserving areas, and changing the limits of integration when you make a substitution. Your homework this week has 30 problems. I think around 20 of them are indefinite integrals. The rest are definite integrals, something like that. So you are now in a place where you can go through and tackle all of those. If there's anything you run into trouble with, of course, you can come see me in office hours or shoot me an email. Is there anything you guys would like to ask before we wrap up the meeting for the day? See something in the chat here. Yes, of course. Yeah, let me go back to those first few pages. Let's see here. As long as I didn't throw them out. Okay, here's page 1. See that light. Okay. Here's page 1 with the lighting. Page 2 was just the reverse of this, yeah. So let's do it like this, and then there's a bit at the bottom here that you'll want. Okay. And then what is the next page? Okay. Alrighty then, if there's nothing else, I'll go ahead and end the meeting here. Please work hard on that homework. The more you practice this between now and Wednesday, the easier the stuff on Wednesday will feel. If you need anything from me, you guys know what to do. Be mindful, exam 3 and the final are coming. They're right around the bend. So make sure you are keeping up with the homework, practicing things, and asking for help where needed. That's it from me. I'll see you guys on Wednesday.